All right, so we're going to be doing two different topics today. We're going to hit up one shots real quick. I meant to do this last class, and well, I forgot because I got distracted by you all complaining about the math stuff, which is fine. And then we're going to come back and hit the math stuff up. All right. So first thing is one shots. All right, now we do need two variables for one shot, and um, this does have two different one shot options. All right, and by this I mean Alan Bradley. Actually, we have three blocks. All right, and these I father's living to outside. So you have your ONS, which is in line with your code. All right, that is basically like a little button input type of thing. So it qualifies as an input. So whenever you're putting those in, it's going to go on the left hand side. All right. Siemens did have this as well, except for they had a value on top and a value on the bottom. Right. Um, so both Allen Bradley Siemens have this. They both overall work roughly the same. All right. The Siemens one only checks one input. All right. So no matter what, like if you had just like a start button and then a one-shot input on Siemens, it only checked the second sensor that you put in. It didn't actually check the value of the start button. So the start button had to be true before that one shot would trigger. Otherwise, the one shot would trigger based on its sensor and nothing would ever happen. In Allen Bradley world, this checks all of the inputs before it. So if you have two sensor inputs, both have to be true before that one shot will trigger. All right, which is kind of nice because then the order doesn't matter. You know, again, if I had a start button and like a limit switch, if the limit switch triggered first, then the start button, one shot would trigger then. If the start button was first, then the limit switch, it would still trigger. All right. Or again, in Siemens world, if the start button was false and then the limit tripped and then the start button was pressed, well, the output would have missed that one shot from the limit switch being pressed already, so we wouldn't have done anything. So both do have their benefit, is really what it comes down to. So with this, the order of where you put it, how far to the left in your code on the line is important, because if you only wanted to monitor one input, put that all the way to the left. All right. Again, with the Siemens one, it didn't matter, but it didn't give you the option to trigger based on two. So I kind of like the Allen Bradley one better. It's a little bit more useful, but I still hate the one in line. I find them to be annoying and confusing, and I just don't like them. All right. So personally, we're not going to go over that one. Which leads us with these other two. So we have our one shot rising and our one shot falling. All right, and those are our two function blocks. Those are our outputs. All right, nothing too fancy there in the long run. So both work the exact same way. All right, so we're just going to go ahead and we're going to do the falling one. So we have a storage bit and we have an output bit. So I just like to call these OSF storage and OSF output. And again, you guys can make them as you like or name them as you like. I'm creating my tags now for them. So I didn't create those ahead of time. All right, so now I have my outputs there, and we can just go ahead and throw an input on here. And we're going to go with start button because I'm using the fluid trainer still. I have my reasons. All right, and then we're just going to go ahead and throw another, we're going to throw a counter on this. Counters, again, just so you guys would be able to see it. Go ahead and follow along with me, guys. It's the reason I have you sitting at your computer so you can actually experience the wonders of the one shot here. All right, so we're going to do that, and then I'm just going to throw the output on here, OSFO. All right, so go ahead and do that, and we'll be back. All right, so hopefully you found those one shots under the bit section on the top. My computer will go. All right, so under the bit, we have our one shot. So in theory, what's this going to do? If you were to download this code to your PLC and hit run, what do you think would happen? Excellent. Every time it let off, it will count up one. So if you guys want to go ahead and start the download process, so that would be good to go. That would be great. All right. But yes, every time we let the start off the start button, our output will turn true. All right. So remember we used a falling here. So when we push the start button in, that goes positive. That one shot is still looking for that falling transition, that negative transition. So we haven't hit that yet, so nothing's happening. And once we do get that negative transition, that is when we'll get that one to go true. It goes true for one loop of code, and then we're done. All right. So we're counting on the release of a button not the press of a button. All right. Wow, this computer's not happy with recording. That's okay. So anyway, remember that one shot. It's since we did a falling, really laggy. It'll draw. Anyway, it's looking for this transition right there. Remember, right? Because we are doing a falling. Right. So looking for that edge. So one shots, Allen Bradley. They're not really any different in the long run than Siemens. All right. You still have an output. You still need a storage. Remember, the whole point of that storage is to remember what it was last loop. All right. As I like to think about it is, you want to know what the temperature yesterday was compared to today. Like, is today higher or lower? You need to know what yesterday's temperature was. All right. Because you have to need something today's temperature to compare to yesterday. You need something to compare to. That is the whole point of that story. All it is. So that is kind of our one shots in a nutshell. All right. So questions on one shots. Anybody? We're gonna move on to some math now. All right. So we're gonna go ahead and create a new line, and we can come over here to our math tab. Of course. This computer does not like. All right. Anyway, go ahead and find math. Compute and math. There we go. All right. So we have a whole bunch of different options. Let me just go ahead and throw all the different blocks and look at them kind of one. All right. So compute, CPT. All right. This is there for the purpose of allowing you to write out a whole formula all at once. All right. It is overall very useful. All right. It's definitely probably the best option in my opinion because it allows you to write the formula like you would expect to write it. All right. Now you put parentheses in, plus, minus, subtract, divide, those types of things, and it all seems to work out okay. Now there are some funky things like how to do a square root there. I'm going to assume is SQRT parenthesis, but I'm not actually positive. I haven't tried that yet. But that seems to be like the standard for square root, right? So there are some options there. So, but anyway, so compute, that's what it's for. Notice we have our destination, DEST, and then our expression. So an expression is where you type out the whole formula. We have add, subtract, multiply, modulo. Okay. So subtract, add, multiply, even divide. I think overall it makes sense. All right. Remember, it's always going to be a math application B. So a plus b, a minus b, a divided by b, a times b. Right. So in this case, order does matter with minus and subtract, or minus and divide. All right. Because a divided by b is different than b divided by a. All right, so it's always going to be A, the symbol, then B. Nothing too crazy there. If you just put 2 into A, 3 into B, and the destination as your variable that you want to store that as, it would be fine. So the destination is always basically the equals blank, and that's where you'd be storing the answer to your problem. Right? So add, subtract, multiply, divide didn't show up, but I like to believe that one's pretty straightforward. Modulo or mod, we've talked about this briefly in class. All right. The whole purpose of this is to display the remainder. Because most of our variable types in Siemens or Allen Bradley don't have decimal places. They are dealing with whole numbers only. Right? Because of that, if you have a decimal, what happens? Well, we just ignore it. So like if you did 12 divided by 12, you'd get 1. If you did 13 divided by 12, you would still get 1. All right? So you're like, well, I need to know that one. I need to know there's a decimal. Well, there's not a great way to display that. Now, you can create variables that are reals, REALs. Those do have decimals. So if you did 13 divided by 12, it would give you 1.09 or something like that. I think it's not sure, but roughly. All right. So you can go to reals. That just means you have to have your data types as reals and things like that, and they're going to take up more memory. So there's always going to be a little bit of give and take going. Now again, in our class, memory, never an issue. Right? You could have every data type be a real, and it would be fine. Or at least whenever it comes to these analog values, we reals. Now, just because you make something a real doesn't mean you're going to get any more precision out of it right off the bat. Like if we took our analog sensors and we just stored them into a real value instead of a dint, we're not going to get any more precision. Analog digital converters are only 10-bit or 12-bit. I don't know what they are, but we can't create more information out of nothing. Right? If you remember when we're using the analog and we're watching the levels, you're seeing like 3,100, and then you see 3,400. It jumps that 300 numbers at a time, and you're like, why did it jump so much? Well, it's because of the analog digital converters built in these PLCs. They don't have a high enough resolution to see a finer degree of motion. Right? So we don't have that option. So just because we convert something to a real doesn't mean we're going to magically get more information out of it. It just means that we now can have a decimal place when you're doing like math equations and like that. It may be helpful to you. But anyway, modulo allows you to get that remainder. So if you did 13 divided by 12 and 1, if I made this, go ahead and just do this. So if we did this 13, not 1, and made this 12, our answer would be 1. All right? If I did 13 divided by 12 here, it would actually be 1 divided by 12 as far as the software is. Because it would say, well, 13 divided by 12 gets us a whole number of 1, and the remainder is 1. All right, that's all modulo does, is it gives you the remainder, which is a very useful thing to have. Sometimes you don't want to deal with decimals. It's just a pain to deal with decimals. I don't want to go there. All right, so maybe just keeping everything whole numbers and doing modulo and getting the remainder is great. For example, if you wanted a distance in feet and inches, right, and we're dividing by 12, you would say 13 divided by 12 is 1 foot, 13 divided by 12 is 1 inch, right? So it will just give that for you. You don't have to then say, oh, I have to take the decimal off of 12 to then multiply that by 12. That's just really free. So modulo allows you to not deal with those decimal places and gets you that nice little rounding perspective. We have a square root command. All right, so hopefully that's nothing crazy. What's absolute value do? Makes everything a positive, not just an negative. All right.
Positive.
Yeah, positive is already positive. But yeah, if you put 2 into that, it's going to spit out 2. If you put negative 2 into that, it's going to spit out 2. All right. And again, that has its purposes. Right. Not going into what all those purposes are, but it has its place in time. So overall, those are our main math equations. Right? Now, remember, when you're doing math, sometimes you do, like 65 divided by 7. And you're like, well, 67 goes into, well, let's do by 4, right? 65 divided by 4. You go, 4 goes into 6 how many times? You'd go 1. So you'd write 1 down, and then you'd say, okay, now 65 is 25, and you'd say 25 divided by 4 is 6. You say 1, so you get 16.5 if you want to continue. But if we had a whole equation, right, we're trying to do a whole lot of math. So you're trying to do like 3 plus 2 parentheses squared times 6 or plus something. Oftentimes when you guys are at least doing it by hand, you're breaking it down into steps. You're saying, okay, we're going to do 3 plus 2 first. That's 5. And you rewrite the equation. And then you say, oh, now we're squaring that. So I would say 25. If you're going to use these non-compute blocks, basically you're going to be doing that constantly, right? Because all you can do is one operation at a time. And that's 2 variables and an output. Not even like, oh, I have 3 plus 6 plus 12 plus 18. That's 4 variables. It's all math, but I only can do 2 variables at a time with an equation and then 1 output. So you're going to be constantly breaking things down into smaller equations, which means we need a place to store something. All right. So if I wanted to do the equation, let's just type it in here just so you see it. Expression. If I wanted to do 3 plus 2 times 4 block is off times 4 you know, and let's go ahead and just divide the whole thing by 3. There we go. We're trying to do that equation. You know, first, go ahead and just put stuff over. There we go. So first you'd say, okay, I need to do my parentheses first, right? So I need to do 3 and 2. And then my destination, I'm just going to call this storage. And I'm actually going to call it storage 1 because sometimes, you know, you might need multiple storages. All right, and then after that, we're going to, okay, now we're going to multiply. So now you're going to throw the multiply block in, and I'm going to say, I'm going to do storage, and we're multiplying that by 4. And I'm going to put that back into storage. All right, you can do that. Yes, we can do a variable equals itself plus something else minus divided whatever. Kind of seems like a crazy round robin type thing going on, but it is completely possible to do. Right? Now you do need to be a little bit careful of that, but we'll come back to that in a minute. And then we'd have to throw one more block in here, and we'd have to do storage divided by 3. And again, now maybe we'd say this is our final output. All right, boom. All right, so it took 3 blocks to do this, and we always had to have that storage place to save our intermediary steps. Right? If we don't have that, you're like, okay, now I don't know that I've completed this step yet. You have to create some sort of temporary storage location. I'm a big fan of calling things temp, T-E-M-P, but that always ends up biting me in the butt because like, oh, I've got temporary this and temporary that, and all of a sudden I'm like, no, which temporary am I using? So maybe not just do temp, maybe do a very something then temp like output temp, storage temp, or something. But you know, one of those things that ends up always nipping me backside because I screwed it up something. But that's okay. So 3 steps to do that equation. Not that big of a deal. It just takes some time to kind of think about, okay, this is step 1. Maybe actually rewrite the equation on your piece of paper as you're doing this so you can write storage in for locations, know what the values are, things like that. It'll just make your life a little bit on the easy. Right? Yes. The compute does follow, you know, please excuse my dear Aunt Sally, PEMDAS. Sorry. So as long as you put your parentheses and everything in the right locations for it, it will do your math as you would expect. Yeah, so this, instead of doing, you know, have output down here, so I would just then throw output here. Boom. So this rung is now equal to that. So I do one rung or the other. Now, the other thing I like to point out is when we're doing math, especially based on variables and things like that, you don't always want to run that math every single loop of code, right? Um, that is just like a disaster waiting to happen, in my opinion, because especially if you're doing something like storage divided by itself is storage or something like that, and you know, if you accidentally delete this math block or you don't put it in there or something like that, your numbers are going to be changing every single time. Even if we only add 1, the storage equals storage plus 1, right? And you just let that run every single loop of code. That's doing 1,000 times a second or more. So, you know, all of a sudden in no time, you're at 1,000, 2,000, 3,000. You're like, what the? Why is my number so big or so small? Because depending on what method. So, you don't necessarily always want your math to run every single time. Right? That can be also be said for the move command. We're doing moves with our analog to make the motor speeds change. You might not want to do your move command every single well because that could get a little hairy depending, right? But it's just something that you do need to keep your eye on. Doing a timer, so just having a timer that loops that is self-resetting, so that way the math only happens once per timer loop when it's done. Great option for yourself. So, you know, you would just basically or after really doesn't matter. Here we go. You know, you just do a little timer there. Not done, but 6 seconds. So there we'd have a self-resetting timer, right? I put 1,000 here. Once a second, now done with it will be true. All I'd have to do is put this down here, make it normally open now, and there we go. Now we have something that only does math once a second. So definitely something you want to keep your eye on. Right now, once a second might be too long. That one do every 10 seconds or something like that. Let's take a random equation where we're like, okay, we want to figure out how much water we pump through our sensors. Right? We have the flow sensor, it spins. We can figure out how much water is flowing past it. Great, right? And yeah, you could run it every loop of code, but then you have to know how long it's been, so that way you can multiply the current speed flow rate times the time, so you can figure out how much has flown through that point in that time period. And if you just do it every single loop of code, which is all I'm finding dandy, but what happens when your code takes longer and shorter, right? Because there's some math equation or something networking happening in the background that's taking more affecting. All of a sudden, instead of taking 1 millisecond for a loop, we're taking 2 milliseconds or 3 milliseconds for a loop. And if you don't have that time frame in there for that multiplication, we have problems, right? Because now that even though we're saying, oh, only one gallon has pumped, well, it might be 1.2 gallons, because all of a sudden our math equations are always a little bit longer than we expected, right? So putting that timer in there to do that loop, saying, okay, every 10 milliseconds we're going to check. This basically says, okay, 10 milliseconds, flow rate is this, multiply 10 by that, and we're done. Now, is that a perfect solution? No, because you are assuming that over that 10 millisecond period, the flow rate hasn't changed, all right? Which may or may not be an accurate statement. So you just need to be careful about that. And anytime you're doing flow and things like that, it's always something that you do need to be aware of. That's in theory why measuring the level of a tank is a better option. Because if you can physically measure how much volume is in there, not if you're counting how much fluid has been pumped in. Because if something's leaking, you also don't know. Little give and take there. So having that perfect example or perfect opportunity here for counting again, only like once every second or whatnot, what I have right now. You can also do a one shot, so that way it's not true for the entire time you're pressing a button. All right, right? If you're like, oh, I need to do math, I need to just press a button, or every time a limit switch comes by, it gets pressed by something, do the math. Well, again, that limit switch may be pressed for a second or two, depending on how long the object is and if it stops and stuff like that. So just because the limit switch is pressed doesn't mean you want to do math the entire time that's being pressed. So having a one shot in front of it to keep that from happening, very helpful. So how are we doing on math? Questions? All right, so when we create tags, normally they go into our programs. So we actually can see values if we go into our tag table, which is really nice and convenient. These, if you ever hit a button like on your PLC and you're saving it, I do a little save action, pops up. It may go, do you want to save the current tag values? All right. So basically it's saying, should we update the save file with all the values of these tags? So that is definitely something that you might want to take into account, especially if you're saving while you're online. That often will. So just be aware of that. Anyway, you can come into in here, and as long as you have integers, there is math here. Pump variable speed. I can just type in a value. Oh, that was not there. Val variable. 56, there we go. So I can just type in. Really, a Boolean too? Oh, there we go. Down here. Let me find the right tag. The third time's the charm, right? Anyway, I can just type a value in here, and it will then save that value as the default value. All right. This is definitely much nicer than this, in my opinion. All right. Some of you guys have had issues where like you turn the key off and everything should stop, but the pump goes into full speed mode, and you're like, what the hell's going on? That's because your pump enable still has a value of 1 in your tag table, even though it's not mentioned in your code at all. That's because your program was running, right? And you said, okay, so you saved values, so your tag table has a 1 there, and then you delete your code that says, hey, pump should be running or not running. So there's nothing to tell the pump to change state anymore. So pump full speed is just on all the time. All right. So you can just come in here to your tag table and you can be like, oh, here, my stop button. No, that, well, you can change your level sensors or whatever. So you can be like, oh yeah, I need my indicator should be on. Should be a 1 value right now. Change it from a 0 to a 1. Very nice and simple. So this is where you can come enter those values that I'm having you guys create here. So you're going to create 4 tags, variable 1 through 4, 5, 7, 0, and 12 for your numbers. You're going to do some math. And then stage 3, we're going to actually use the compute module to do it, just so you guys can compare apples to oranges, so you can do both. And then stage 4 is going to have some other stuff happening, but let's just go ahead and start stage 1 through 3 at this point. Yeah, a full screen this for you guys. Huh. Why can you see this desktop now? That's annoying. That's okay. All right, so let me freeze this, and then you guys can get to work on this assignment.